So let's talk about how to actually learn the parameters of these networks. And we'll start by defining a cost function and then optimization algorithms and so on, right? I was going to check, just to calibrate my expectations, how many of you are familiar with the gradient descent algorithm? Okay, so almost everyone. Not quite everyone, almost everyone. Okay, great. So here's our neural network. And if you have binary classification, then you have a single output unit. And in that case, your neural network will be outputting a value, h of x, which is going to be a real number. And if you have a k-way classification, as we're talking about just now, then with a one versus all learning algorithm, you will have the hypothesis that outputs vectors that are in, let's say, R4. And so given a training set, you can define sort of the natural cost function. This would be a sum over your training examples of 1/2, the difference between the output on your ith example and your actual label, say. And for this example, and if you have multiple output units, could be right. So just squared error output, or again, for those of you that are familiar with like cross entropy or log loss. In practice, we tend to use that more often because it seems to make the problem slightly more convex, but I suspect that in practice, it'll all work about the same. This defines a cost function, and one way to optimize the cost function is then gradient descent. I guess looks like, 90% of you are familiar with gradient descent, but here it is, given initial set of parameters, we're going to keep on reducing the parameters until hopefully we end up at a minimum of the cost function. In pictures, here's gradient descent where you are trying to minimize the cost function, j of theta 1, theta 2, and we have two parameters. Let's call them theta 0 and theta 1. We initialize the parameters at a random location, and we repeatedly take steps downhill until we end up at a plateau or a local minimum. And as you know, if we're to initialize at a different location, we can end up at a different local optima. Okay? So I guess that's gradient descent, where repeatedly we update every parameter as the parameter minus the partial derivative with respect to the cost function of each of the parameters. Right? So for a neural network, in order to compute the gradient, so in order to implement gradient descent, if you have a neural network with a huge vector of parameters theta, right, you need to compute the partial derivative with respect to the parameters of your cost function. And so I think, as Jan had mentioned yesterday, there's an algorithm known as the backpropagation algorithm for doing this. Right, so given a complicated function, you want to minimize this as a function of theta. And so in order to implement backprop, we need to write code to compute the cost function, which is relatively straightforward. You just implement code to do that. And you also need to implement code to compute those partial derivative terms. It turns out that in the deep learning literature, maybe kind of one point of debate and sometimes controversy is whether or not to use higher order optimization algorithms. So some of you may know of algorithms such as conjugate gradient, right? Also BFGS and LBFGS. Also algorithms like gradient descent with line search. We can use things like the Wolf condition as the termination condition. And it turns out that all of these more advanced optimization algorithms, what you need is also software to compute the cost function and the derivative of the cost function. And then algorithms like conjugate gradient, LBFGS, and so on are black box optimization algorithms. So that if you provide to it, software for computing the gradient and the cost function, then these black box optimization algorithms, conjugate gradient, LBFGS, and whatnot, can just take it from there and go try to optimize your cost function for you. So on problems that run on a single machine, if everything can fit in, if you're running everything on a single machine, I personally tend to use LBFGS, and I find it seems to do well relative to gradient descent. But then there are also others that may be better than I am at tuning gradient descent that will prefer gradient descent. So this is one thing that's debated back and forth a bit, I guess.
Well,
Go ahead.
The question is stochastic versus batch.
Stochastic for sure. Yeah, stochastic gradient descent versus batch gradient descent, right?
Right.
If you're doing gradient descent, then you might as well just use stochastic. But if you're doing LBFGS, then do large mini batches. That's what
slows you down.
Yeah. Anyway, for LBFGS, sometimes it works well, right? Young skeptical. Okay. So that's the backprop algorithm. And again, if when you need to implement it, you can get it out of a textbook or get it out of the online tutorial, with the URL given the notes, whatever. But it's not terribly difficult to implement, and the output of it is that you end up computing all the partial derivative terms that you need to implement gradient descent. Okay, the correctness proof of backprop is somewhat complex, I guess. But anyway, so in terms of practical, just again, what I do is just I feel like very often when people like me teach these algorithms, there's often a gap between what you learn versus your experience of actually implementing these algorithms. So I thought I'd share with you. So at Stanford, I've worked with a lot of students, probably in the low hundreds of students at this point, to help them implement learning algorithms, neural networks, backprops, and so on. And in terms of getting your learning algorithm to work, in terms of getting your implementation of backprop to work, there's one little trick called gradient checking, which has been, when a new PhD student joins Stanford, and they're trying to get backprop to work, the most reliable predictor for whether or not they actually get it to work, in my opinion, has been whether or not they do this thing called gradient checking. And so if you're implementing any of these learning algorithms for the first time, if you actually implement gradient checking, which I'll explain in a second, the odds of you having a correct implementation of whatever algorithm you're using will be dramatically higher if you do gradient checking. So let me just quickly share with you what this gradient checking thing is. So just pulling out my notes. So the idea of gradient checking is that after you've implemented backprop, which supposedly is giving you a computation of the gradients, let's just find a different way of computing the gradients and verify that backprop really is giving you the correct gradients. Oh, and it turns out that if you've implemented backprop before, you may know it's possible to have plenty of buggy implementations of backprop that will learn, right? So you implement backprop and there's a bug, but when you run it, it'll learn. It'll do something reasonable. Your learning curve will show that the algorithm's learning. You test on a test set, it'll kind of do something reasonable, but it won't work as well as a correct implementation of backprop. And the reason that hurts is because you've implemented this algorithm, you're hoping to beat the previous state of the art so that you can write a research paper. And if you don't happen to know that you have a buggy implementation, just across the board, all your applications just work a bit worse and you fail to get the good results, just because of a bug that's almost impossible to find. I've seen all sorts of bugs in backprop. You can I personally, most recently, I accidentally replaced an addition with a multiplication somewhere. I don't even remember where, and the algorithm worked fine. All right, so here's gradient checking. Here's the idea. I'm trying to minimize the cost function j of theta. And so what we're going to do is numerically compute the gradient, right? So we're going to, let's use a red pen. So let's say that your current setting of parameters is theta is over there. So we're going to move a bit to the left, find theta minus epsilon, move a bit to the right. Let's call this theta plus epsilon. And so if that's theta, if you evaluate the function at theta minus epsilon, evaluate at theta plus epsilon, and then look at that slope is a very good approximation to the derivative of the function at theta, right? And so the slope of the line is, this vertical divided by horizontal. So there's a j of theta plus epsilon minus j of theta minus epsilon, and divided by this magnitude here, which is 2 epsilon. Okay? So let me just write this out. So we have that d theta of j of theta is going to be very close to j of theta plus epsilon minus j of theta minus epsilon divided by 2 epsilon. Okay? Where, right. And so the way you actually implement this is, I tend to use MATLAB and Octave. So the way you actually implement this in MATLAB is you actually write that piece of code at the bottom, right? You have a function j, so it turns out it's much easier to get a correct implementation of your cost function j than to get a correct implementation of backprop. So having implemented j, you would actually write this piece of code in MATLAB or Octave or Python or whatever, and use this to numerically compute the gradient. And epsilon, I usually set to something like 10 to the minus 4. There's a large range of values that work fine, so it's not too big and not too small. If you numerically compute the gradient this way and verify that it is giving you the same value as whatever backprop is giving you, this will dramatically increase your confidence in the correctness of your implementation of backprop. So right now, whenever I come up with a new model, whenever think of a new neural network model with like a different nonlinearity, a different pooling function, different cost function, whatever, every time when I implement gradient descent, I always do gradient checking. And just as a side comment, if you remember your calculus class from way back, right? This is the alternative formula, like a one-sided difference formula for approximating the gradient. And in practice, this seems to work. This will work okay, but it works less well. So in practice, tend to use the two-sided difference formula in order to numerically compute the gradient. It turns out that the error of the approximation of the formula on the left is on the order of epsilon squared, whereas the error of the formula on the right is on the order of epsilon. So the formula on the left actually gives a much more accurate estimate of the gradient. Okay? So let's see. So when you have a n-dimensional parameter vector, you basically do the same thing on each of your n dimensions of the parameters. So here are the numerical approximation formulas for what the partial derivatives look like. And so you would just implement this, right? So, just step through the formulas quickly. Partial derivative with respect to theta 1 is, you have theta 1 plus epsilon here, theta 1 minus epsilon there. Whereas if you want to approximate the partial derivative with respect to theta 2, you have theta 2 plus epsilon there, and theta 2 minus epsilon there, and so on. And so this is MATLAB pseudocode, I guess. In MATLAB, you would actually, if you have an n-dimensional parameter vector, so if theta is in Rn, you would actually implement this. I'll give you a minute to just read through the pseudocode, but this is looping through each of your n parameters and repeatedly increasing or decreasing it by epsilon and computing the numerical gradient, right? And so grad approx is the numerically computed gradient, and I guess defect, that's what backprop gives you. And it's just verify that these two things are similar, and when that's true, then you probably have a correct implementation of gradient descent. Okay? Just raise your hand if this makes sense. Yeah, all right, cool, great, thank you. And then finally, implementational note. This is how you do this, which is, so the most common mistake I see in implementations of this method is if people continue to do numerical gradient checking even when you're running the algorithm for real, right? So it turns out that this routine for numerical gradient checking is very slow. You should run this only once to ensure that your code is correct, and then you should turn it off forever and be done with it. And so what you do is implement backprop to compute the gradient. then implement numerical gradient checking, make sure they have similar values, and then the important step is to then turn off gradient checking and to use only your backprop code for learning. Okay, and so in the tutorial on the website, there's a programming exercise which should take about 10 minutes to run. And sometimes I get emails from people saying, gee, it doesn't take 10 minutes to run, it took me like 24 hours to run this job. And when I get emails like that, the most common reason is if they were doing numerical gradient checking on every single step of the algorithm. So numerical gradient checking is code that you write and run once only to make sure that backprop is correct. But then when you're doing the actual training, you should turn off the numerical gradient checking and just run backprop, okay? Because backprop is much faster than the numerical gradient. So that's how you implement backprop and make sure that it's correct. Let me just go over a couple more details of how to get these things to work. When you're implementing a neural network, you should be sure to initialize your weights randomly. And here's why. So, I guess in MATLAB, this fmin-unc is an implementation of LBFGS. If cost function is code that computes j of theta and computes the partial derivatives with respect to j of theta, then fmin-unc and other functions in MATLAB Octave implement these sorts of black box optimization algorithms that will automatically search for parameters data for you to drive down the cost function, right? And so, question is, if you're using any of these algorithms, LBFGS, conjugate gradient, or gradient descent, how do you initialize the parameters? So one natural choice would be to initialize the parameters to all 0, but some of you, if you've worked with neural networks before, I guess you already know that this is not a good idea. If you were to initialize all the parameters to be equal to 0, let's see. It turns out that if you look at this weight and that weight, it turns out that after one step of gradient descent, those two weights will remain the same. And here's why, I guess. If you've initialized all your parameters to be 0, then initially your two hidden units, so these two hidden units will be computing the same function of the input, right? And it turns out that, kind of by symmetry, you can show that, let's call these two weights W1 and W2. The partial derivative with respect to W1 of the cost function will be equal to the partial derivative with respect to the second weight of the cost function. And so when you perform a weight update, let's say W1 gets updated as W1 minus the learning rate times this, right? And when you perform the similar weight update for W2, after each weight update, you find that the weights W1 will be equal to W2 still. And thus, on the next iteration, you have that, the two hidden units are still computing the same function of the input. Run gradient descent, the two red weights will continue to be identical to each other. And moreover, via a similar argument, this blue weight and that blue weight will always have the same value as each other. And this magenta weight and that magenta weight will always have the same value as each other as well. Okay? So no matter how long you run backprop. And so what this means is that no matter how long you run gradient descent, your two features, A1 and A2, are both computing the same function of the input. So you're learning only one feature. So you may have 2 hidden units in the spectrum, you may have 100 hidden units, but all 100 hidden units are computing the same feature. So it's not a very useful representation. Okay? So symmetry breaking in for neural networks refers to the process by which we initialize each weight to a random value, maybe a random value between minus epsilon and epsilon. And this serves, we call this, I guess, symmetry breaking, and it serves the purpose of ensuring that your hidden units start off computing slightly different functions than each other, and thus that as you run backprop, that they will eventually learn, hopefully learn to compute very different functions from each other. Okay? So, finally, let me put everything together and talk about how to do this in the supervised learning setting, which I know some of you are already familiar with, and then we'll get on to the unsupervised feature learning settings a little bit. Okay? But so taking all the pieces we talked about, if you have a supervised learning problem, so let's say you have a large label training set, the first step is to pick a network architecture, right? And this means, to pick by architecture, I mean the connectivity between the neurons in your network. So, in this example on the left, we might call this a, what? We might call this a 3-5-4 architecture with 5 hidden units. This is like a 3-5-5-4, and this is 3-5-5-5-4. And it turns out that empirically, so the number of input units is kind of constrained. If you have 3 inputs, you have to have 3 input units. If you have 4 classes, you have to have 4 output units if you're using a one versus all encoding. And your flexibility is in choosing the number of hidden units per layer, as well as choosing the number of hidden nodes per layer, right? So just be clear, if you have 4 classes, if you have k equals 4 classes, then your output units are using these sorts of, right, one versus all encoding, and so you have 4 output units. And so long as you do regularization, let's see. Right. Oh, and so when choosing the architecture of a neural network, there are all these parameters, right? So first, how many hidden layers do you choose? Do you have 1, 2, or 3 hidden layers? How many nodes per hidden layer should you choose, right? So people have all sorts of ways of choosing these things, and sometimes this has led to part of the feeling that these algorithms have way too many parameters and it's hard to tune these parameters. So what I want to do is just give you a reasonable default. When I don't feel like tuning a lot of parameters, this is how I choose a number of hidden units, number of hidden layers, and so on. This is a reasonable default. If you have, so let's see, choose the number of hidden layers to be, let's say 1, 2, or 3. People rarely set numbers much larger than 3 hidden layers. Some people do. But so you need to make that choice. And then a reasonable default would be to have the same number of hidden units per layer, but to set that to be as large as possible, right? So this is one of the interesting things about these neural networks is that for the most part, the larger you can build the model, the better it will perform. I think I showed this on the earlier slide as well. And what this means is that the number of hidden units becomes I think of it as a computational parameter, I guess. If you make a poor choice of the number of hidden units, the price you pay is that your algorithm runs a little bit more slowly, as opposed to that the price you pay is that your algorithm ends up performing worse, okay? And so if you're trying to design a neural network for the first time, and if you just need something, what's your first choice? I would use 1, 2, or 3 hidden layers, and then just have have the same number of hidden units per layer, and just set that to be as big as possible, and that would be a perfectly reasonable default to start with. Okay. Sorry. All right. So, and then putting together the steps you need to train a neural network. Here they are. First, you randomly initialize the weights. And then, implement forward propagation to compute. Forward propagation is the name of the algorithm that computes the outputs given any new input x. Implement code to compute the cost function. Implement backprop to compute the partial derivatives. And then and then do gradient checking, and then repeatedly use forward prop and back prop. Implement back prop and gradient descent basically. Step 5, implement gradient checking to make sure that your numerical derivatives are correct. And then disable gradient checking once you're sure that you have a correct implementation. And then finally, run the optimization algorithm for a long time and until hopefully it converges. Okay, and so that's it. And if you do these steps, you have a working implementation of backprop. And neural network learning is technically a non-convex problem, and people talk about how neural nets are non-convex. But I suspect that, the latest folk wisdom is that if you have a massive neural network with a lot of hidden units, then these days many of us think that non-convexity is less of an issue, and that the bigger challenge is the network getting stuck on plateaus, so very flat regions of space where it's hard to make progress. But you implement this and train it for a long time, you'll be able to get state-of-the-art results on a lot of problems if you have lots of label data. So this is a autonomous driving example, and this was done by Dean Pomerleau at CMU. When I play this video, you see a few things, I guess. So on the lower left is the camera input. So the goal was to train a neural network to drive a car, right? On the lower left is the camera input to the neural network. Up here, in this bar, is shown the driving direction that was selected by a human driver. So a human driver, in this example, selected the driving direction shown by where the white region is. So in this case, human driver was steering slightly to the left, looks like. And this second bar down here shows the output of the neural network, shows the steering direction selected by the neural network. And the steering direction is indicated in this visualization by the location of where the white bar is, okay? So when I play this video, you actually see, live training of a randomly initialized network. So initially, it outputs a random steering direction, has no idea how to do it, but then, and then the network will train, and then you see the process of, this is exactly gradient descent. You see the network, learn and adapt over time.
Alvin is a system of artificial neural networks that learns to steer by watching a person drive. Alvin is designed to control the NavLab,
Can you hear the audio?
a modified Army Humvee equipped with sensors, computers, and actuators for autonomous navigation experiments. The initial step in configuring Alvin is training a network to steer. During training, a person drives the vehicle while Alvin watches. Once every 2 seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction. This training image is reduced in resolution to 30 by 32 pixels and provided as input to Alvin's 3-layered network. Using the backpropagation learning algorithm, Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random. After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver. This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving. 12 times per second, Alvin digitizes an image and feeds it to its neural networks. Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. steering direction from the most confident network. In this case, the network trained for the one-lane road is used to control the vehicle. Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises. When its confidence rises, the two-lane network is selected to steer, safely guiding the vehicle into its lane on the two-lane road.
Yeah. That was a backprop supervised learning. In relatively short order, we're going to be able to adapt. So that was just supervised learning, right? Learning from labeled data. In relatively short order, we're going to be able to adapt these algorithms to learn from unlabeled data. Okay, and I'm going to do that in just in like the next 15, 20 minutes. Oh, actually, before I do that, I think on the handout, I think you can now do questions 12 and 13. Why don't you take a second to do that, and then we'll jump into the unsupervised learning stuff. D, cool. And actually, have people finished, or who has an answer to 13? No, people are still thinking. Okay, fine. Keep thinking about 13. All right. Call the answer. What do you think 13 is?
D.
D. All right, cool. Did I hear F? No. Okay. Good. Yeah, cool. All right. So it doesn't work. Just now, this question on any advice on choosing a learning rate. Boy, the online tutorial goes into greater depth on that. But the way I usually choose the learning rate is you plot the cost function J that you're trying to minimize, and make sure that the cost function really is going down. If the cost function, is not going down, it means your learning rate is too big. You can try a range of values until it is too big, and then back up a little bit is what I usually do. So search on a logarithmic scale or an exponential scale until it's too big, and then divide that by, 3 or something. That's what I usually do. All right, so let's talk about learning features from unlabeled data. So I'm going to first describe an autoencoder, and then talk about how the users learn features. Okay? So let's say you have unlabeled data. What can you do, right? There you have no labels to try to get your neural network to predict. An autoencoder is a particular type of neural network in which we're going to have the neural network learn to predict the input values. Okay? So here's the idea. Let's say we have images or something, and these are, I guess, 6-pixel images that have inputs x1 through x6. What I'm going to do is build a neural network with one hidden layer, and I'm going to set the target outputs to be equal to the inputs. So I wanted to just reconstruct the input. Okay, so here's an image. Please set the neural network parameters so that you just get me back exactly the same image as was input. So this is called an autoencoder. After training this network, what we're going to do is we're going to lop off the output layer. Just gonna go to the output layer and get rid of that. And we're going to take the feature values computed by the hidden units as our feature representation for this image. Okay? So it turns out that if you train a standard autoencoder, just as I've described it, it won't work well. But there's one modification which makes this actually learn useful features, and that is sparsity. So during training, let's constrain my hidden units to be sparse. So I'm constraining my hidden units to mostly output values near 0. I don't have time to go into the mathematical details of this. The equations are written out on the online tutorial, but it's basically add one term to your optimization cost function, to your cost function j of theta. Just add one extra term to your cost function, that penalizes your features A1, A2, and A3 being non-sparse. You want your features to be close to 0 as often as possible, right? So the cost function is exactly the sum of two terms, is how well can you reconstruct the input, that's the autoencoder cost, and then the second part of the cost function is the sparsity cost. It turns out if you train an autoencoder, then one layer of a sparse autoencoder will, very reliably get you features that look like this. So the algorithm will invent edge detection just like sparse coding does. I think, the algorithms like autoencoders, sparse autoencoders, sparse coding, ICA, they all do fairly similar things. It's kind of, there are different implementations and different implications for running time, but all of these algorithms end up with substantially similar edge detectors. Question?
But this time you don't have more sparse image than input. It's not over complete, right? Because that's not like.
Oh yes, right. And in this diagram, I drew it as though I have 3 hidden units, so I have fewer features than input pixels. If computationally, if you can afford to do so, if you have 6 input pixels and a dozen features, that usually works even better, right? This is also why sparsity is needed. If not for the sparsity constraint, then if you have 12 hidden units, it's an under constraint problem, right? It becomes trivial to reconstruct the input by learning the identity function. But even if you have, 6 inputs and a dozen hidden units, so long as you impose a sparsity constraint, there are still non-trivial solutions, and those non-trivial solutions will correspond to learning these sorts of edge detectors. Okay. Right, and so just to be clear, what this visualization is showing is, let's train a sparse autoencoder, and let's visualize what the first feature A1 is looking for. And it turns out maybe feature A1 is a feature looking for that edge. And now let's visualize, what the second feature A2 is looking for. And this may be a visualization of the second feature. And then let's visualize what the third feature is looking for. And the third feature is looking for a third edge, like so. Okay, so that's what the visualization is doing. So in other words, this algorithm has again invented edge detection, where each of the features you've learned is trying to detect a different edge that may or may not appear in your image. Now that we've extracted a bunch of features using a sparse autoencoder, we now have a better higher level representation of the input image. And so what you can do is say, gee, instead of representing my input using the raw pixels, let's use these features, A1, A2, A3, that I just learned to represent my image, right? Because now you have a new feature vector, A1, A2, A3, that represents the image in terms of what edges appear in the image rather than in terms of what pixels appear in the image. And so if you have a classification problem that you want to solve, if you want to detect cars versus motorcycles, you can now take these 3 features, A1, A2, A3, and feed them into a support vector machine or logistic regression or some other classifier. And this will often do better than if you were able to, than if you did not have these better high-level features available to your algorithm. Okay? So just to say it again, right? Again, from purely unlabeled data, you can train a sparse autoencoder. We all have an infinite amount of data, right? So you can train a sparse autoencoder on a massive amount of data, learn great features, and then having done that, you can take those features, even if you have only a small amount of labeled data, you now have vastly superior features with which to train your logistic classifier. Okay, so the autoencoder, that thing shown on the left, those features can be learned using just unlabeled data. And then this, on the right, you can do with your labeled data. So the setting where this sort of thing can work very well is especially if you have a ton of unlabeled data and a relatively small amount of labeled data, because this is an algorithm that can exploit massive amounts of unlabeled data that you have in either semi-supervised learning or self-taught learning settings. Okay. Then there's one other cool thing you can do. I think either Yoshi Benjo or Jeff Hinton was the first to do this, I'm not sure which. Or maybe it was Yang, I'm actually not sure. Which is the idea that instead of doing this in 2 steps, you can take these 2 neural networks and let's just put them together, right? And now it's all one big neural network. And you can now take the label data you have and run backprop through this entire neural network and update all of your parameters using this neural network. Does it make sense? So this is something that's called unsupervised pre-training plus fine-tuning. Unsupervised pre-training refers to the process of where you take your unlabeled data and you train a sparse autoencoder, and you come up with that using your unlabeled data, right? And, or you can take labeled data and do it ignoring the labels as well. But it turns out that this really works well in the regime where you have a ton of unlabeled data. And then what you do is you then add on the logistic classifier. Now with all of these parameters initialized from the unlabeled data, you can now throw in these parameters as well. So the parameters I'm circling in green, you would just randomly initialize. And this gives you a neural network, and you can then just train the entire neural network, the red and the green parameters, all the parameters, using your much lesser amount of labeled data. Okay, and so the second process of running backprop through the entire network is called fine-tuning. That's how you can do this using using a network with one hidden layer. And it turns out if you do this, this will often outperform, especially if you're self-taught learning or have a lot of unlabeled data, this will often outperform purely supervised learning. I guess this two-step process works really well when you have massive amounts of unlabeled data and a relatively small amounts of labeled data. Then this really, it turns out that if you have a large amount of labeled data, right, if you have a ton of labeled data, then there's less to gain by using unlabeled data. And so you find that semi-supervised learning and self-taught learning algorithms have the biggest advantage when you have relatively little labeled data and a ton of unlabeled data. Whereas in contrast, in settings where you have a ton of labeled data, then often what works best is if you just do it as forget about the unsupervised learning phase, just take a neural network and train the heck out of it, and often that'll work as well as anything else, and the learning phase adds relatively little. Yeah?
In those situations where you have a large amount of labeled data, do you still use backprop on deep networks?
I do, yes. So if you have enough labeled data and if you have enough patience, backprop on deep networks often. So I think, what's his name? Jürgen Schmidhuber was training networks with like 7 layers or something using just straight backprop. He trained on a GPU for a long time, and it worked just fine. And so it turns out that if you compare unsupervised pre-training followed by backprop compared to only backprop for the same number of backprop iterations, then if you initialize with unsupervised pre-training, often that does a little bit better. But I believe that if you take your entire computational budget, if you have a fixed computational budget, and if you have a large amount of labeled data, if you take, meaning if you have only a fixed amount of patience to wait for your machine to run, then in regimes where you have a ton of labeled data, if you just put all of your computational budget in backprop supervised learning, I've rarely seen performance to be better if you spend less time on the supervised learning and more time on the unsupervised learning. But this applies only to the settings where you have a ton of labeled data, right? Cool. So that was the one-layer version, and then now let's talk about the deep learning version. So here's what you can do. Here's the so this is my one-layer of sparse autoencoder, right? So this particular version was first done by Yosha, but it really uses ideas due to Jeff, I think. Well, actually, first one with Yosha and Jan, I guess. I'm not sure who, whatever. But so what you can do is train a autoencoder like so to get, your features H1 through H4 is what I'm calling them, right? Now, let's go ahead and lop off the output layer. And you now have the features H1 through H4 for representing your image, Now let's train another sparse autoencoder, but now taking this H1 through H4 as your new representation. Okay? So here's an autoencoder which takes as input H1 through H4 and tries to reconstruct H1 through H4. And it tries to learn a new, even higher level representation, which now has superscript 2. I guess I've gone from superscript 1 to superscript 2, right? And so the hope is that if this first set of features are learning edges. The hope is that this next set of features will be learning combinations of edges. And then you can repeat this process. Having learned these features, H superscript 2, you can then now have a high-level set of features to feed to your logistic regression classifier or softmax classifier or whatnot to make a prediction. Yeah?
And the heuristic for choosing widths in this type of setup?
As big as possible. And so once again, having done this in 3 separate steps of learning features, then classifying, you can take these 3 networks, as I've drawn them here, and put them together. So those are the 3 networks I had, and you can imagine if you lop off these output layers and just put these things together, right? Then you end up with one network, with a single neural network. There's a deep network trained for multiple layers of representation to do your prediction. Okay? And so with all that machinery of supervised learning, backprop, neural networks, and so on, with these, you do need to figure out how to implement the sparsity. That's something I didn't talk about, but modulo that detail. You now know how to learn deep layers of representation and get these things to work. And so with that, I think could you do questions 14 and 15 in the handout, and then we'll wrap up for the session. So what's the answer to 14? C. All right, awesome. And 15? T. Okay, cool, awesome, great. We should break for lunch, and then after lunch, so I know for some of you, some of the material I was doing over right now was fairly basic. In the last hour that I have with you after lunch, what I'm going to do is jump back to the high-level bleeding edge topics and talk about more recent things, talk a bit about language, talk a bit about scalability, about that CAT result that some of you know about that we did at Google. And also, I know that many of you, like I said earlier, some of you are here because you want to apply these algorithms to problems. Some of you are here because you want to do research in deep learning or advance the state of the art. And so the last thing I want to do in the next hour is also share with you some of my thoughts and philosophy on, and maybe try to give you the advice that I give to my PhD students when trying to do research and pushing forward, and how to go about thinking about some of the problems you encounter when you're trying to advance or use some of these algorithms. So we'll do that after lunch. Thanks. See you later.